Today we're going to talk about linear phase filters. As I had mentioned in the last video, sometimes some filters have the property that they will delay all the cosines passing through them by the same amount. And this is useful in a lot of cases. In those filters we call them linear phase filters. Right. We know we call them linear phase because the group delay is going to be constant. Now, we call them linear phase, right, because the phase of the frequency response is going to be a linear function of omega. And of course, when we calculate the group delay, it's going to give us a constant, right? If this is a linear function, well, and the group delay is just going to be tau 0. Now, when we talk about linear phase, it's going to be a property of the frequency response, right? It's the phase of the frequency response that's a linear function of omega. Now, how do we translate this to a property of h of n? Because when we design filters, we might work in frequency, but we can also work with h of n, the impulse response. So what property does h of n have to have so that the filter is linear phase? Now let's start out with our definition, and let's say h of e to the j omega is the frequency response, and let's write it as amplitude and phase. Now let's assume, or let's write, that this is linear phase, right? Our phase is going to be a linear function of omega. Now, we can use the inverse Fourier transform to find h of n, right? This is the definition of our inverse Fourier transform, or inverse DTFT. And if it's linear phase, it's going to look something like this. And so h of n is going to look like this for our linear phase filters. Now, let's do something. Let's take and substitute n for 2 tau 0 minus n, and let's also take the complex conjugate. Okay, so when we substitute n for 2 tau 0 minus n, right, there's only one n over here. So this n here we would substitute for 2 tau 0 minus n. And then we also put the complex conjugate above. Now when we do that, the complex conjugate of course changes the sign of all the terms. And let's break this into two terms. And we see that these terms, we can add them together. And the result is the exact same function we had up here for h of n. In other words, for a filter to be linear phase, h of n must be equal to the complex conjugate of h of 2 tau 0 minus n. Okay. Another way of saying this is that h of n is symmetric around tau 0. Now, 2 tau 0 minus n is inside the argument of h of n. So it has to be an integer, right? N is an integer, so 2 tau 0 must be an integer 2. Now, if 2 tau 0 is an integer, the only way we can have that, tau 0 must be an integer or an integer plus 0.5, right? It could be something like 3, for example, or it could be 5.5, right? 3 times 2 is 6, 5.5 times 2 is 11, but they're all going to be integers. Now, if tau 0 is an integer, we're going to have a symmetry that looks like this, right? It's going to be symmetric around tau 0. And this value here is going to be this value here and so forth. And we're going to have some symmetry around that central point of tau 0. If it's symmetric around tau 0 and tau 0 is an integer plus 0.5, it's going to look something like this. These two values are going to be the same, and then these two values are the same, etc. Now, let's keep adding to this. So we know for it to be linear phase, it has a certain symmetry. Now we also know typically we want our filters to have other properties. Most importantly, causality. And if you think back to when we were talking about systems, right, causal systems, one of the properties that we saw was that for a system to be causal, its impulse response must be 0 for time less than 0, for n less than 0, right? The impulse response is the response of a system to an impulse at 0. And so before 0, we can't have anything coming out of the system because we haven't given it an input yet. So let's say, right, h of n is 0 for n less than 0. Let's say we have a causal filter. And let's say we're going to have both properties. We want a system to be linear phase and causal. So if it's going to be linear phase and causal, it must have the symmetry, it must be this, and it's going to have causality. Now, if we have this symmetry right here, h of n equals h of 2 tau 0 minus n, if we substitute n equal to 0, it means that h of 0 is going to be h of 2 tau 0. So at 0 and at 2 tau 0, we basically have the same value. Okay. We can take the complex conjugate, but in most cases we're talking about real filters, so this is going to be real. It also means that because all the values for n less than 0 are 0, it means that all the values for n greater than 2 tau 0 are also going to be 0. Okay, let's look at that. For example, if tau 0 was 2, now to be causal, all the negative values over here would have to be 0. Because of symmetry, the value at 1 and the value at 5 have to be the same. The value at minus 2 and 6 are the same too. So if all of these are 0, all the values from 5 onward have to be 0 too. If it's symmetric, for example, with respect to 2.5, then the value at minus 1 and at 6 are going to be the same. The value at minus 2 and 7 are going to be the same. And so we have, again, a symmetry, but if it's going to be causal and all the negative values of n are 0, it means that at some point our h of n is going to be 0 again. Now what does that mean? It means that all causal linear phase filters are going to be what we call finite impulse response, right? They can't go on forever. If they start somewhere, they have to end somewhere too to have that symmetry, right? Because if they go on forever in one direction, they would have to go on forever in the other direction, which would make it an infinite impulse response. This is the reason why finite impulse response filters can only be made in the digital world. Analog filters can never be finite impulse response. So linear phase filters only exist in DSP. They don't exist in the analog world. So I want you to go through, I want you to do some homework problems of what was discussed today. I'll basically repeat what we did above for some different filters.